Alright, today we're going to be discussing reaction stoichiometry, but more specifically we're going to be discussing it in terms of limiting and excess reactants. So to start, we're going to go ahead and define a limiting reactant, which can be defined as the reactant that has the smallest stoichiometric amount in a reactant mixture and consequently limits the amount of product in a chemical reaction. Alright, so let's go ahead and put that into terms that everyone can understand with an easy example such as pizza making. If we were going to go ahead and make one pizza, let's say that it would require us to have one crust, 2 cups of cheese, and then 5 pepperonis, and that would give us one pizza. So let's say that we have a whole bunch of ingredients out on the counter. We've got 2 crusts, we've got 4 cups of cheese, and we have 8 pepperoni. So what we found earlier was that if we need 5 pepperonis per pizza. So this means that we can still only make one pizza because we're limited by the number of pepperonis we have because we only have 8 out of the 10 required. So we have an excess of 1 crust, 2 cups of cheese, and 3 pepperonis. In our pizza equation, it means that we're limited by pepperoni. So you can take that exact same example and apply it to chemistry. So let's go ahead and start off with a basic problem. So we have a sample of 2.0 grams of ammonia, and it's mixed with 4 grams of oxygen to form nitric oxide and H2O gas. The question asks, what is the limiting reactant and how much excess reactant remains after the reaction is stopped? So the first thing and foremost extremely important is to always begin with a balanced equation. And our problem is already given to us. So we have 4 moles of ammonia plus 5 moles of oxygen, which goes ahead and reacts to evolve into 4 moles of nitric oxide and 6 moles of H2O gas. Now, in most problems, it's really important to remember that you need to, it doesn't matter what product you choose, either ammonia or H2O, but it's nitric oxide or H2O, but you must stick with the same product throughout the entire problem so that you can compare it to your reactants. So, we're going to go ahead and proceed to step 2 once we have a balanced equation. Step 2 just involves converting grams of the reactants into moles of the reactants. Also, during our specific example, keep in mind that we divided this one equation up into 7 steps, so we're going to be proceeding into separate steps, and so we're not going to be doing the calculations throughout the entire thing. We're going to do it all at one time at the end. So, for step 2, you want to go ahead and begin with the initial amounts of grams, so 2 and 4 grams, as listed up in the problem, and convert those to moles. So 2 grams of ammonia, and we know that there's 17 grams of ammonia per 1 mole of ammonia. So that allows us to proceed to step 3 now that we have moles of the reactants. But first, so you take the moles of the reactants, or moles of ammonia, and you realize that according to the equation, you have 4 moles of ammonia for every 4 moles of nitric oxide produced. So that grants you the moles of the product. So now that step 3 has given us the moles of the products, we can proceed to step 4. Step 4 allows us to take moles of the product and convert it to grams of the product. So you've got 4 moles of nitric oxide, and we know that for every 1 mole of nitric oxide, we get 30 grams of nitric oxide. So when we take this whole entire equation and we calculate it all the way out, we find that for every 2 grams of ammonia, we have 3.53 grams of nitric oxide produced. We can do the exact same thing to oxygen, and then for any other problem, however many reactants you have. So beginning with 4 grams of oxygen, you convert the oxygen into moles. You take the moles of oxygen and convert it into moles of the product, and then convert moles of the product into grams of the product. And that leaves us with 3 grams of nitric oxide. So what the significance of this numbers is that for the reactants, whichever one produces the least amount of the product becomes the limiting reactant. So in our case, it's going to be oxygen because it only produces 3.0 grams of nitric oxide. Let's go ahead and put this back into perspective and go back to our pizza example. We realize that even though we can make one pizza, we cannot make 2 pizzas because of the limiting reactant pepperoni, but that still leaves us with excess reactants of 1 crust, 2 cups of cheese, and 3 pepperonis. So that will go ahead and lead us into our final set of steps, which is now that we know the limiting reactant in our equation, we want to go ahead and calculate the excess reactant, which is going to be ammonia. So when you're trying to calculate the excess reactant, you begin with our limiting reactant, oxygen. So you begin just like we did in step 2 by converting the grams of the limiting reactant, oxygen, into moles. And then also you'll take the moles of the limiting reactant and then compare them to the moles of the excess reactant, ammonia. So now that we've got moles of the excess reactant ammonia, we can proceed to step 6, which is calculating grams of the excess reactant. So, beginning with your 4 grams of oxygen, you convert it, the limiting reactant, you convert it into moles of the limiting reactant, which then you convert into moles of the excess reactant into grams of the excess reactant, which goes ahead and totals at 1.70 grams of ammonia, the excess reactant. But the process does not end there. This is the amount of ammonia that did react fully with all of the oxygen. What we want to find is the excess, the amount of reactant that's left over after all of the oxygen has evolved. So we do that by processing the amount of the original sample of ammonia and subtracting from it the amount of ammonia that reacted, and that'll grant us our excess ammonia. So 2.0 grams of ammonia, which was stated in the problem, which is the original sample, minus 1.70 grams of ammonia, the amount that reacted fully with all of the oxygen, and that leaves us with 0.30 grams of excess ammonia. So there you have it. That's how you go ahead and find the limiting and the excess reactants. But it's always important to remember to start with the balanced equation, always cross out your units and make sure they cancel out, and that if you ever get confused, you can always just refer back to your pizza reference.